Here is a question on general organic chemistry. Read. Let us first understand the key concept here. 4-pyrone is a cyclic compound with an oxygen in the ring and a carbonyl group at the 4 position. When it reacts with a proton, acid, the most stable cationic product arises from protonation at the site that gives maximum resonance stabilization. Moving on to the next step. 4-pyrone has 2 oxygen atoms, the ring oxygen, position 1, and the carbonyl oxygen, position 4. Protonation can occur at either oxygen. Moving on to the next step. Consider protonation at the carbonyl oxygen, position 4. If the carbonyl oxygen is protonated, C is equal to O becomes CO with positive charge on oxygen. The resulting cation can delocalize the positive charge. The resonance structure would show the ring oxygen donating electrons into the ring, generating a fully conjugated 6-pi electron aromatic system. The structure becomes O+, ring oxygen with H. Wait, let me reconsider. And for the final step. Protonation at the ring oxygen gives O+, H in the ring. But protonation at the carbonyl oxygen gives C is equal to O plus H, which via resonance becomes C plus O, and then the ring oxygen lone pair can donate to give a fully aromatic beryllium-like cation with 6 pi electrons. The 4H pyrene 4-1 protonated at carbonyl oxygen gives a hydroxypyrrhelium cation. When the carbonyl oxygen of 4-pyrone is protonated, the resulting species, 4-hydroxypyrrhelium, has the structure ring oxygen at position 1, C is equal to C double bonds at 2, 3 and 5, 6 positions, and CO plus at position 4. The ring oxygen lone pair contributes to make a 6-pi aromatic system analogous to beryllium. This gives exceptional stability. Option C shows a 6-membered ring with oxygen at position 1, ring O, neutral, a fully conjugated diene system, double bonds at C2, C3 and C5, C6, and the exocyclic oxygen at position 4 bearing a positive charge with an H attached, O plus H. This corresponds to protonation at the carbonyl oxygen, giving the hydroxypyrrhelium cation, a stable 6-pi aromatic species. Option A shows protonation at the ring oxygen and disruption of conjugation, sp3 carbon present, losing aromaticity, not the most stable product. Option B shows protonation at a ring carbon, breaking conjugation, highly unstable, not preferred. Option D shows protonation at the ring oxygen, O plus H in ring, with full conjugation. While this would give a beryllium-type cation, the positive charge on the ring oxygen is less stable than the hydroxypyrrhelium where protonation is at carbonyl oxygen giving delocalized charge through the ring with the ring O donating electrons. The most stable cationic product is the hydroxypyrrhelium cation formed by protonation at the carbonyl oxygen, which is shown in option C. Therefore, the correct answer is C. Therefore, the correct answer is option C.